Hello and welcome back to Mechanics Applied to Aerospace Engineering. Today's lecture will be dedicated to the momentum and energy of a rigid body. This video will be shorter than previous ones, but it will be quite math intensive. Our purpose is to derive the expressions for the linear momentum, angular momentum, and kinetic energy of a rigid body, expressions in which the inertia properties of previous lecture will make their appearance. I also want to spend some time giving you a first glimpse on the dynamics of rigid bodies, where all these quantities will be present. In all three cases, the quantities that we are going to study will be defined in terms of integrals over the whole body. So let us start with the first one of them, linear momentum. This one doesn't present any difficulty. Basically, the linear momentum of a rigid body is the sum, understood as the integral of the linear momenta of all the differential particles in the rigid body. Okay, so if we write the contribution of the momentum of a differential particle in this way, we have to integrate over the whole body to get the total linear momentum of the body. All right. So, of course, the contribution of a single differential particle can be expanded as the product of the velocity of that particle times the mass differential. If we remember the definition of the center of mass from previous lecture, which is basically the first moment of the mass distribution divided by the 0th moment of the mass distribution, then we can write the integral of the position over the whole body times the mass differential, which is basically the first moment of the mass distribution, as the total mass of the body times the position of the center of mass. If we take time derivatives in this expression, we see that the product of the mass times the velocity of the center of mass is basically the integral that we are looking for. So that is our linear momentum of the rigid body. And that's it. We basically conclude that the linear momentum of the rigid body is equal to the linear momentum of a virtual point particle that has the same mass as the rigid body, that is located at the center of mass and is moving like the center of mass. Okay, so for everything that has to do with linear momentum, we can glob all the mass of the rigid body in a single point. That point is the center of mass, and it works. Okay, we have that the linear momentum of that particle defined in that way is equal to the linear momentum of the whole rigid body. Regardless of whether the body is rotating or not, the linear momentum always has this expression. It always has this form. The expression of the angular momentum is quite more involved than the previous one, but it can be defined in a similar way. Before we do that, let us take a look at the drawing on the right, because it's the drawing that we will use in the following slides as well. So we start with a reference frame S0, which is the reference frame in which we are computing the quantities. Okay, so this, as you can see, has for the angular momentum has the subindex 0. That means that we are considering velocities with respect to this reference frame when defining this angular momentum. Apart from that, we are going to define two other reference frames. Okay, so we have a reference frame SA, which is just an auxiliary reference frame with the same vector basis as S0 that has the origin at point A, where point A is the reference point about which we are computing angular momenta. Okay, and then we will also have a reference frame SG, which again is a parallel reference frame to S0. It has the same vector basis, but the origin of this reference frame is located at G, the center of mass of the body. All right. So that said, we can define the angular momentum as the integral of all the contributions of all the mass differentials to the angular momentum, which can be expanded in this way. All right. This is the angular momentum of a small mass differential moving with this velocity as seen from point A over here. All right, so this is what we are going to sum over the body. That's where the integral comes from. We are integrating over the whole body this expression, where point P is a point that varies as we move over the body. Remember that this way of writing the vectors, RPA, is totally equivalent to this other way. Okay, so if it helps, in your case, you can think of those vectors as with this nomenclature. All right, so the vector RPA is just the vector that goes from A to P. All right, so how are we going to expand this integral? What we want to do is to process this definition of the angular momentum of the rigid body about A in a way that we can reduce the integral to known quantities. And in particular, we will see that the inertia properties of last week will appear. So in order to get there, we are going to replace this velocity, the velocity of the point P that runs over the whole body as we integrate, we are going to expand that with the velocity field of the rigid body. So we will use the velocity at point A. Okay, here we have to be careful because in general, the point of the rigid body that happens to be on top of A, which is a geometric point of a space, okay, may not be the same velocity as the point A itself. Right? So imagine that this body is rotating at some instant, a particular point, for example, that one may be over the point A, okay? But the geometric point A may have a different velocity than the point of the rigid body that happens to be on top of point A. That is the nomenclature that we introduced in previous videos. Okay, so armed with this expression for the velocity field of the rigid body, we can substitute this velocity, obtaining this result. Okay, so here observe that we have two integrals. In the first integral, since the velocity of point A of the rigid body is a constant inside of the integral, I have already taken it out of it. All right. So we have these two integrals. The first of them involves the integral of the position vector from reference frame SA, and that is clearly the first moment of the mass distribution of the rigid body in reference frame SA. So this will become, after we integrate, this will become the position of the center of mass as seen from reference frame SA times the mass of the rigid body. The second integral involves a double cross product, which we are going to expand. So as you can see, on the first case, we have, as I promised, the mass of the rigid body times the position of the center of mass as seen from A. Okay, according to our other nomenclature, this is vector AG. All right, and if we expand this double cross product, we have the first vector times the third, then the second, that gives us this, and then we have the first times the second times the third, that gives us this with a minus. All right. Now, we still have to process this a little bit more. Clearly, the first term has already solved the integral, so there are no more integrals to deal with over there. But here we are still have the integral of these two terms. So let's see how we can rewrite this. So first of all, regarding the first term, observe that I can introduce a unit tensor anywhere that I want, because a unit tensor is the diagonal matrix with ones that doesn't affect at all the result. So I can write that just like this. Okay, and perhaps now you see where I'm going. I'm involving tensors. The second term is a little bit more difficult, but hopefully you see that it doesn't matter if I place this here or here, it's exactly the same. All right, and if you remember, when we introduced the tensor product, we said that it was basically a dot product in the weighting. Okay, so you can check term by term that this expression is actually the same as this other expression. All right, basically what we have here is a different way of writing the dot product of omega with the position vector on the right. Okay, so now that we have that, we can rewrite this remaining integral in a slightly different way. Okay, so that way of writing it is this one. And here you can identify the definition of the tensor of inertia of the rigid body about point A. Okay, so that is basically what this long integral means. It's just the product of the angular velocity vector, okay, which is a constant inside of the integral and you can take it out of the integral, times the tensor of inertia of the rigid body. Okay, so with this result, we have been able to replace this integral with this, and this integral with this other one, which in the end becomes this. That means that we can write the final expression for the angular momentum of the rigid body about a point A as the sum of these two terms. Okay. Now, clearly this result is valid and you can apply it in whatever point A that you want, but usually we will only apply this in two particular types of points. Okay, we will be careful with our selection of the point A. If we choose our point A adequately, we will get rid of this second term over here. Hopefully you can see that there are two possibilities that we can apply to make this second term equal to 0. The first one is to pick a point A such that it is a fixed point of the rigid body. That means that the velocity of the point A parenthesis B, okay, the point of the rigid body that happens to be on top of A, is always equal to 0. If that is the case, it is a fixed point of the rigid body in reference frame S0. Then we get rid of the first term and we just see that the angular momentum is the tensor of inertia about A times the angular velocity vector. All right. The other possibility is to choose our point A, about which we are computing the angular momentum, to be the point G, the center of mass. In that case, the vector AG over here is 0, and also the second term vanishes in that case. In that case, we write the expression just like this. Okay. The result that we have just obtained is not the only way that we can process our integral. So let's go back to our definition in terms of the integral of the differential angular momentum, and let us apply a different expansion to the integral. So in this case, what I want to do is to rewrite the vector AP over here as the vector AG plus the vector GP. Okay, so in other words, I want to decompose this vector as the vector AG plus the vector GP. Okay. Apart from that, we are also going to use the expression of the velocity field of the rigid body, but in this case, our reference point will be point G. All right. So let us replace these two vectors with these expressions. And when we do that, we get the integral that you see over here, which, if you expand the cross product in the middle, gives you a total of 4 different terms, as you can see. All right, so we have this one times this one times this, then the first one times this, and then this times this. All right, so each of these terms can be dealt with in a different way. Observe that inside these integrals, the velocity of g is a constant. It doesn't vary in the integral. And the same happens with the position vector ag. Okay, this does not involve the point P, which is the one that runs over the rigid body as we integrate. So this is basically a constant that can be taken outside of the integral. So in the case of this first part, we can replace everything with this result. Okay, we have the constant cross product can be taken outside of the integral, and we have just the integral of mass. So that term gives us that quantity. In the case of the second one, Vg can be taken out, and what we have is the first integral, the first moment of the mass distribution. So we can write that in this form. Okay. So this is constant, it comes outside, and this is what remains inside of the integral. Observe that this integral gives us the position of g, but since we are measuring from g, the result will be the vector gg, so that's 0. Okay, so this second integral doesn't contribute anything to the result, it's always equal to 0. In the case of the third integral, we have this double cross product where this vector and this vector are constant inside the integral, so we can take them out. And what we have is again this integral of rpg, which will be 0 because it will give us, again, the position of g as seen from g. So that is the null vector. So again, this integral does not contribute as well. And finally, we have this last term over here, okay, where we have that everything except for omega b0 depends on the point of integration. Okay, so how can we process this? Well, first thing that we are going to do is to observe that if we write the velocity of any point p from the viewpoint of the reference frame as g, okay, we can use the velocity field expression, but the velocity vector g as seen from g is equal to 0. Okay, so the velocity field expression in that case becomes this. All right. So we can replace this parenthesis over here with the velocity of p as seen from reference frame g. All right. When we do that, we obtain this expression, which by comparison with the definition of the angular momentum at the beginning, we can identify that this is the angular momentum of the rigid body about point G as seen in reference frame G. Okay, so I'll say that again. This is the angular momentum of the rigid body about point G in reference frame SG using velocities of reference frame SG. Okay, so with these partial results, we can gather everything together and we can write the following. Before we do that, I also wanted to note that the quantity that we have just obtained in the last integral, okay, can be expanded a little bit. So observe that this velocity vector that we have over here can be expressed as the difference between the velocity vector in reference frame 0 and the velocity of the center of mass in reference frame 0. Okay, we can do this because the two reference frames S0 and SG are parallel. Okay, they share the same vector basis. They are not rotating with respect to each other. All right, so we can always do that. If we now expand the result, we have this integral and this integral where again this quantity will be 0, right? And this result is important because it allows us to conclude that the angular momentum about G in reference frame SG is the same as the angular momentum about G in reference frame 0. All right, so we have this equality. This only happens for the center of mass in general. So finally, gathering everything from the previous slide together, we have this expression. This expression is useful because it allows us to relate the angular momentum about the center of mass of the rigid body with the angular momentum about any other point of space, okay, a point A, like that. All right, and we conclude that this equality can be understood in the following way. The angular momentum about an arbitrary point A is equal to the angular momentum of the rigid body about its center of mass, which is basically due to the rotation of the rigid body as seen from the center of mass. Okay, that is what we call hg0, plus a term that is equivalent to the angular momentum of a point particle with the same mass as the full body, located at G and moving with G. All right, you see that this second term over here is basically the angular momentum of a point particle located here, moving with the same velocity as the center of mass and as seen from the point A. All right, so this is the interpretation that you can give to this formula. The last quantity that we are going to introduce today is the kinetic energy of the rigid body. And again, we have to compute this quantity as an integral over all the contributions of the differential mass particles that we have in the body. Okay, so again, remember that we have the drawing from before. We have the reference frame SA, S0, and SG. All right, so there are several ways that we can expand this formula, just as with the formula of the angular momentum. The first one is to take the velocity of P and use the expression of the velocity field of the rigid body as you see it over here. All right, so just as before, we consider an arbitrary point A of the rigid body. Okay, just to make sure that we mean a point of the rigid body, we use the parentheses as before, and we apply this expansion inside this square. All right, which of course we can write as the dot product of VP with itself. When we do that, this is what we have. All right, so this is going to yield a total of 4 terms. All right, when we process the dot product. Now, 2 of the terms, when you multiply this times this and then this times this, are identical, so you can gather them together. All right, so you can write this as just 3 terms. The first term appears from the dot product of VA with VA, which is constant inside of the integral, and therefore we can just write it as this. Okay, the integral that remains is the integral of mass, so that yields the total mass. The second contribution, which is this cross between this and then this times this, since it appears twice, it has a 2 in front, and that eats away the 1/2. And basically, since the velocity of A is constant inside of the integral, and the same happens with omega b0, we can take them out of the integral, and we just have this. As always, when an integral of this type appears, this is related with the definition of the center of mass. In this case, we are measuring from point A, all right? So we can replace this integral with this. And finally, the last integral involves the square of this quantity. Okay, so let us see how we can process this. One possibility is to use this vector expression where we have 2 cross products and then a dot product in the middle. You can expand this in this way to obtain the following result. All right, so you have the dot product of omega with itself, the dot product of RPA with itself, and then this other term over here. Now, just like before, we can introduce a unit tensor whenever we want, the identity tensor, right? So in particular, I want to do that on the first term, which I will write like this. Okay, you see, I have put together the dot product of RP with itself as this quantity, all right? And then in the middle, between the dot product of omega with itself, I have inserted the unit tensor, which doesn't change the result at all. All right, so this is an identity. Regarding the second term, all right, using the properties of tensor products, this double dot product on the left and on the right can be rewritten in this way. Okay, so we just gather together the 2 position vectors with a cross product. And again, I leave as an exercise to you to check that these 2 expressions are identical, component to component. Okay, so again, you see where we are going. This is going to involve a tensor of inertia, and indeed it does. When we gather everything together, we see that we basically have the terms that define the tensor of inertia, except that they are multiplied left and right with the angular velocity vector, each of them. Okay, now since the angular velocity vector is constant inside of the integral, we can take them out, and the final result can be expressed in this simple and compact manner. Okay, so hopefully after this slide and the ones on the angular momentum, you see the value of the tensor of inertia. It is basically a shorthand for a complicated integral, okay, which we can compute once and then use it for many different purposes. So in the case of the expansion that we have applied here to the kinetic energy, you see that we can write it as the sum of 3 terms. The first one is this one, the second one is this one, and the last one is this. All right, let us gather everything together in this new slide. So here you have the result that we have just obtained. Okay, and like before, this is perfectly valid. You can use it in any point A to obtain an expression for the kinetic energy, but clearly you can make some simplifications if you choose the point A which you use to expand the integral in an adequate manner. So in particular, again, we have the same two possibilities as before. If we choose a point A of the rigid body that is fixed in S0, meaning that its velocity is 0, then this term and this term will be 0. So we just have something very simple. We just have that the kinetic energy is the kinetic energy associated to the rotation about point A, the fixed point A. All right. So whenever there is a fixed point in the rigid body, that is a clear choice. The same happens with the definition of the angular momentum. If you have a fixed point in the rigid body, you can choose that point to compute your angular momentum, and clearly you will have simpler expressions. The other possibility, which is the one that we usually take when there is no fixed point on the rigid body, is to choose the center of mass as our point to expand the velocity field. All right. When we do that, the vector RGA, so the vector that goes from A to G, vanishes because A is G. All right. So we only have two terms, which are the two that you can see over here. All right. Now, as we will see in the next slide, this has a nice interpretation. The kinetic energy of the rigid body can be decomposed into two contributions. The first term over here is associated to the rotational kinetic energy about the center of mass, and the second term is associated to the translational kinetic energy of the whole body concentrated on the center of mass. So the kinetic energy of an equivalent point particle located at the center of mass with the same mass as the rigid body and moving like the center of mass. Now, to complement this derivation, and similarly to the case of the angular momentum, we are going to obtain an alternative expansion of the integral. So we go back to our definition of the kinetic energy in terms of the integral, and here what we are going to use is directly the velocity field of the rigid body supported on point G instead of any arbitrary point A. Right? So when we do that, we observe that we can expand this square over here in the following way. So we have three terms, just like before, but in this case, the terms are this one, and this one. So when we integrate, the first one is a constant, so that doesn't pose any problems. We just have the integral of mass, and we get that. The term over here, okay, with the 2 in front of it, the 2 actually vanishes with the 1/2. So it can be expanded as you see, okay, so Vg is a constant, the same happens with omega inside of the integral. So the thing that remains inside the integral is Rpg, which gives us the position of G as seen from G, and again that is equal to 0 as we saw in other similar integrals in this lecture. And the term in the middle is the square of the cross product between omega and Rpg, okay, which is very, very similar to the term that we had in the previous slide that eventually gave us the tensor of inertia. All right. So this is basically the square of the velocity of the rigid body as seen from reference frame SG. Okay. Remember that the velocity of any point P as seen from reference frame G can be expressed as the velocity of G with respect to G, which is 0, okay, plus omega B0 cross Rpg. All right. So basically what we have here is the square of the velocity of any point P on the rigid body as seen from point G. All right. So this is the kinetic energy of the rigid body as seen in reference frame G, and we call that Tg. Okay. So this is a useful result by itself. Okay. What we have is that we can relate the kinetic energy in reference frame 0 to the kinetic energy in reference frame G, okay, the parallel reference frame that has the origin in G instead of on O, all right, and the difference between them is this additional term, all right. So if you relate this with the result from the previous slide, it's clear that Tg is 1/2 of omega B0 dot the tensor of inertia about g dot omega v0. All right, and we conclude again that the kinetic energy of a rigid body has two contributions: the rotational one about the center of mass plus the translational one of the center of mass. All right, so we have seen a number of expressions. Here in this slide, you have the main results gathered together for quick reference. We will use these expressions, these expansions of the linear momentum, angular momentum, and kinetic energy of a rigid body extensively in the following lectures. In the second part of the lecture, I want to take a first look with you at the equations of the dynamics of a rigid body. Our starting point is the only equation of motion that we have, which is the equation of motion of a single point particle, which you see over here. All right. So with this, we have to construct all the equations of the dynamics of the rigid body. The way to do that is to consider, instead of a regular point particle, a differential point particle with a differential mass. Okay. So if you think that the mass is a differential quantity and the amount of force that this particle receives is a differential force, you can use that expression and integrate over all the particles of the rigid body, obtaining what you see over here. Okay. So the left-hand side is the product of the acceleration of a particle that runs over the full body inside of the integral. Okay, P again is a point that moves over the full body as we integrate. Okay, so the left-hand side is that times the mass differential, and then we can rewrite that taking the derivative associated to the acceleration outside of the integral and keep the velocity times the differential of mass. All right. The right-hand side is just the integral of all the forces, the sum of all the forces acting on the body. So if we focus our attention on the left-hand side, it's clear that what we see over here is the derivative of the linear momentum of the rigid body as we have defined it today. Okay, so a different way of writing that derivative is as the derivative of the velocity of the center of mass, which is just this. Okay, now this is very convenient. This means that if we if we sum the equation of motion of all the particles in the rigid body, we get a similar expression that basically refers to the dynamics of the center of mass of the rigid body. Okay, and that will be our first equation. This doesn't pose any difficulty. We just have that the translational dynamics of the rigid body are given by the dynamics of the center of mass under the effect of the resultant of all the forces acting on the rigid body. Okay, so if we sum together all the forces acting on the rigid body and we replace the rigid body with a point particle with the same mass located at g and moving as g, then we have an equivalent problem. The derivation of the equation of the rotational dynamics of the rigid body is a bit more involved, but it still begins with the only equation that we have, the equation of motion of a point particle. In this case, we are going to take the cross product with the vector AP, where A is some point, okay, and P is a point of our rigid body. So this is our vector AP. Okay, so we take that cross product on the left-hand side and on the right-hand side of our equation. Of course, the right-hand side, by definition, is the torque of the force Fpi about point A, and we call it like this. All right. In the following, we are going to focus on the left-hand side only. All right. So observe that this term, this cross product, can be expressed in the following way. So we see that the acceleration here is the derivative of the velocity. Okay. We can take the derivative sign outside of this cross product, all right? But then we have to take into account that AP may have a derivative, all right? The derivative of API in reference frame 0 is equal to the velocity of PI minus the velocity of A. All right. So when we put everything in place, and I ask you to check this as a small exercise, you will see that in order to recover exactly what you have on the left side of this equation, you need to add this extra term. Okay, there is another term which is VPI times VPI that vanishes because it is the cross product of a vector with itself. All right. This is, by the way, an expansion that we already did when we were looking at the angular momentum of a point particle. So when we put this into the integral, okay, we have to keep all of this inside of integral because it depends on point P, which is the point that varies inside of integral. In the case of the second term over here, VA is a constant, and we can keep it outside. All right. Clearly, this is a quantity that we already know. All right, which is the velocity of the center of mass of the rigid body times m. Right. Now, by definition, this is how we define the angular momentum of the rigid body about point A. Okay, so we can replace it by that symbol. This is, as we were saying, the mass times the velocity of g. Okay, and finally, what we have is that the left-hand side can be expressed in this way. All right, so you see that whenever we try to take moments on the equation of motion to get the rotational dynamics equation of the rigid body, the angular momentum of the rigid body will appear very naturally. Okay. Just as always, when we have this type of second term on our expressions, we can try to get rid of it by choosing carefully the point A about which we are computing the moments. Okay, so if we take a point which is a fixed stationary point of the rigid body, then this will not appear. All right. Another possibility is to take the center of mass, because then we have that A is equal to G, right? So we have velocity of G times the velocity of G, and it also vanishes. Lastly, I want to give you a first taste of the equation of the mechanical energy of the rigid body. As before, we have to start with our only equation, okay? And in this case, in order to get anywhere, we want to dot multiply that with the velocity of the point. So on the left-hand side, what we have is this dot product, which can be rewritten in this way. Okay. Again, I leave this as a small exercise to you. Just write the velocity over here in terms of 3 arbitrary components and check that indeed you can gather this dot product inside of the derivative like this. Okay. On the right hand side, what we have is the dot product of the force with the velocity, and that is by definition the power of the force. Now, if we consider a differential mass, okay, a particle with a differential mass, the left hand side can be expressed like this. Okay, we have the derivative sign, which can be taken outside of the integral. And on the right hand side, we have the power, the integral of the power of the point particle. Okay, we are integrating over the whole body. So P again is the point that runs over the integral. And on the right hand side, we have the power of all the forces acting on the body. So by definition, what we have here is the integral of the kinetic energy, right? So what we see is the derivative of the kinetic energy of the rigid body as seen from reference frame 0, okay? Now, I don't want to get any further at this point with these derivations, okay? In the next lecture, we will see properly the equation of the dynamics of the rigid body, both the translational and the rotational equations, and also the equation of the mechanical energy. All right. Just to conclude, observe that if the right-hand side is equal to 0, or if it can be expressed as a function of a potential term, then we can obtain an equation for the conservation of the mechanical energy as the sum of the kinetic plus the potential. All right. So that's all for today's video. Thank you, and see you next time.